Hello, today we'll talk about the configuration space. These are the today class objectives. Basically, we'll talk about before we talked about the brief touch on the configuration space, but today we will mainly talk about some of the definition examples related to the configuration space. Also, I already uploaded the chapter related to this configuration space at this my book webpage. So probably, if I remember correctly, chapter 4 actually corresponding to these issues. And then last time we talked about the classic motion planning approaches, including roadmap, cell decomposition, also the potential field. Yep. And then also I went over some of your questions. One of your fellow students asked that are there all the path planning algorithms solved by the graph navigation problem? So in the class, we mainly talk about somehow they're given basically they're starting from the C space, which is discretized space, free space with this graph, and we do the graph search, right? That's one of the very common approach, but there are many other approaches. Also, there are many other these problems. So another technique is the trajectory optimizations. Also, there are trajectory optimizations. This technique does not use the graph-based approach. Instead of it used the optimization techniques. Recently we also published. We will present this paper at the coming IROS, and then basically over there we need to we have this fetch robot, and then we need to move the robot arm, the manipulator, to exactly follow this red line. As you can see, we are able to follow this red line from here to there actually. So if you click this link, you can see the video. But to do that actually, we use the trajectory optimization instead of this graph-based approach. Mainly because so over there we can also use the graph-based approach, but it's very slow. Instead, we are actually using optimization to follow the goal, this line in a correct way. So basically, I'm not giving the usual answer to the question since the question itself is very broad. But I'd like to just give one actual response to this question. If you're interested more, I recommend you to Google along this topic. Also, I also went over your paper summary. Most of them are very good. For example, one of you actually presented. Do the summary from the paper from the ICCV. Even though it's vision paper, he or she able to find the paper related to some sort of the trajectory optimization. That's fine. Also, there are many some of the machine learning some of this reinforcement learning technique. Other one. Also this kinodynamic motion planning. I hope that I can briefly touch on this reinforcement learning in the class. But also one of you also present this paper. Learning patch reconstruction for accelerating the multi-view stereo. It's from the CVPR. But when I look at the actually abstract summary of this paper, I wasn't able to see the clear connection between this paper and the path plan, the main theme of our course. I recommend you to write down I recommend you find the paper that are related to that are related to our course theme. Or at least write down the connection between this paper, also the main theme of our course. So now let's talk about today's materials here. So basically here, these two examples here, we just assumed a very simple this box robot here, and then we wanted to move this box robot while avoiding the collision against this environment from here to there, right? Also, this is another cases here. Actually, we used this linked robot here, the one joint, another joint, and so on. So it seems like we actually had these two joints, and then we are moving this kind of linked robot from here to there, and so on. So the motion planning, we wanted to design motion planning algorithm that can actually easily apply to the diverse set of robot without changing a lot of this underlying algorithm. Along that line, the main idea of the DC space actually becomes one of this key ingredient. So basically, I briefly touch on the DC space differ, but the C space, the configuration space mainly represents the degrees of the freedom. In other words, the parameter of the robot. the DOF, degree of freedom DOF of the rigid robot, articulate robot, and so on in a point. So basically, whatever robot you have, basically once you represent the parameter or the degrees of freedom of your robot in the C space, basically there any shape of your robot in the workspace represented by a point in the C space. And then we applied our various algorithms in that C space in addition to the workspace. So when you're performing collision detection, obviously you need to actually specify the robot in the workspace, and then you need to do collision detection. So at one point you need to have the clear idea of this workspace. But actually, if you are using the C space, you can represent this diverse set of robot in a very simple way. So also I showed this one, this workspace. This here also the linked robot. Actually, this point there are only one joint, but this point actually fixed within the workspace. And then here actually this one joint. Basically the orientation here or the orientation, there are two degrees of freedom, right? And then we represent that C space here. There is actually one joint, another joint, and then this shape, this configuration mapping to here, and another this orange shape actually mapping to there. Then the finding collision free path from here to there is nothing but finding path from this point to there within the C space. And then this shaded area actually at that configuration, if we place the robot, here and there, if you place this upper arm to there, we will have collision, right? We cannot go there, right? And then basically we want to find the path from here to there without having any collision. Then basically path plane nothing but finding this collision free path. So again, here I will give the formal definition. The configuration of robot is nothing but a complete specification of the position of every point on the robot. So far we actually specified that it's a rigid robot, right? Then at that case we just assume we already know that this implicit shape of robot, right? And then only the parameter is that this angle, that angle, right? And obviously when you have the deformed robot, we need to encode more in the C space, but for the simplicity, we just assume the simple robot, the rigid robot here. And then the configuration is not basically the usually configuration of robot space expressed as a vector or as a vector of the containing this position of your robot or orientation of your robot. And then within C space, the configuration is nothing but a point. And then C space basically represent all possible configuration that your robot can have. For example, this is a manipulator grounded here. We can have the one joint here, theta 1. This the angle of this joint, one parameter. There's another joint, so another angle, theta 2. These theta 1, theta 2 actually the two parameter DOF of your C space, right? And then in the end, but when you do manipulate this one, we need to worry about the end effector, right? For example, to pick this robot, somehow we find the angle here, and then we place our end effector so that we can grab it, right? So a lot of cases we control the theta 1, theta 2 to place the end effector at a particular location in a particular heading, particular orientation, and so on. So if we just suppose that our algorithm only care about the position, end effector position in the workspace, right? And then there could be some of the ambiguous situation. For example, given this end effector pose, there could be many different many different configurations. For example, within this end effector position, you can have this shape or that shape, right? There could be the multiple configuration. Then it will be a little bit ambiguous for us to do the motion planning. So that's why this is one of the reasons why we're using the C space to plan our robot. In other words, we change the angle. We actually move around our robot to place our end effector at a particular location in the workspace. So again, just considering this position of end effector is not a valid C space. And also you can think that actually we can exchange theta 1, theta 2, right? And then basically the space of C space, we can treat that. I mean, there a lot of cases actually to simplify our thinking or the explanation. We are just using this Cartesian 2D Cartesian space, right? Theta 1, theta 2. But actually, as you know, when you're rotating from here to when you're rotating this angle, starting from 0 and 2 pi, then it will be actually wrapped around here, right? So the more in an exact way. So think about it. Basically, we are moving. We can change the theta 1 in that direction, right? There's one circle, right? And then at a particular position, we can also move around this joint in this 360 angle, right? And then at that position, we can also move around here. So actually, our C space, when you are looking at this topology of C space, then instead of this two Cartesian space, you usually have this torus shape. So there are a lot of there are certain this research that's thinking about the topology of the DC space. But in this class, we are not going to talk about a lot of issues of topology. But I'd like to show this example so that you can aware of that. We cannot. I mean, there are a lot of cases we're just using these 2D Cartesian spaces for simplifying our discussion on the DC space. But that's not the exact view of our C space. For example, in this case, torus. Okay, so now let's look at what are the relations between workspace and C space. Suppose that we have this kind of obstacle in the C, obstacle in the workspace, and then our robot has this kind of circle. It's the center of our robot. This actually has certain radius, this one. And then to compute this C obstacle space where we have collision, then one easy way is that we roll the circle from here to there, right? And then when you are looking at the center position of when you are looking at for example, this actually our DOF in our DC space, XY position. Then if you look at the trajectory of the center of our circle, then if the center is located there, if we place the robot if we place the center of robot there, we will have collision, right? So actually this is showing the boundary of our C obstacle. Within this space, we will have collision, right? And then basically now let's look at this case. Here, same very similar situation here. This workspace, this obstacle, and then in this case, we assume that the point robot. Then the C space, basically just the XY portion of this point, right? And then when we place this point robot in the obstacle, the boundary, we will have collision. Basically, we are touching the obstacle, right? And then basically, C obstacle space exactly looks like this workspace. In this case, our DC obstacle space mapping to this obstacle in the workspace, right? But as we increasing the radius of this circle, then you can see that the C obstacle space getting larger and larger, right? In this case, basically we actually assuming very big circle. Then here actually the C obstacle space very wide. Then for example, if you want to move this robot from here to there, then we cannot find any path from here to there, right? So that's assuming that also there's the wall. Then we cannot move this robot passing through this region. Then basically, as you can see, as the robot getting bigger and bigger, basically there are actually our free space getting smaller and smaller. In other words, the C obstacle space getting larger and larger. Okay, so also we can think about it. What are the dimension of our C space? So the dimension of our C space is the minimum number of the parameter. Minimum number, not just number of parameter, minimum number of parameter needed to specify the configuration of the object completely. And then at that case, the minimum number of the parameter is called the number of the DOF, degrees of freedom of that robot. For example, suppose that again the rigid robot. And then here we can actually move around this reference point. We can treat that as x and y. So basically, if we know the reference point, we can specify this robot in the workspace, right? And then also we require this orientation, this orientation, the heading of your robot. So at that case, in this parameterization, we can think about it x, y, and theta position, the 2D position, also this orientation. Theta actually has this particular range. And then you can see that this actually 3D configuration, 3D space in our C space. But one can use the different parameterization. For example, same x and y, but you might remember that here. Let me write down. So for example, one can actually represent the orientation robot something like this. You can specify the unit circle, and then basically the orientation of the robot can be specified at a certain point in the UV, right? In the UV position in this unit circle, right? In that case, you might remember that since UV in the circle, we actually have this kind of equation, and then you might recall that U actually has cosine theta and this sine theta, right? In this case, this is theta, the orientation. Then we know that the UV coordinate, right? And then one can use the x and y, the position of your robot, UV, as an orientation, right? Here actually we're just using the four different parameters, right? Looks like it's a four parameters. It looks like it's a 4D space, but as you can see, to define UV, we just needed the theta, right? So in the end, the dimension of C space is not a 4, it's a 3, since we need to think about this minimum number of this DOF. So in other words, basically dimension of the configuration space should not depend on the parameterization. There could be many different parameterization, but we need when you think about this parameter, the DOF, degree of freedom, we basically the robot actually here, even though it looks like they are 2D, robot cannot move around that direction, right? Since only the orientation can move along in that space. That's why there's only 1D space in terms of the freedom of orientation. Also, there could be the many different constraints. Back then, also early in the class, I talked about different local, global, that kind of constraint. Also, there could be the many other constraints. One of the common constraints is the holonomic constraint. For example, here, suppose that this kind of the pendulum that are linked to the particular point. This actually certain length is L and theta, and then this pendulum motion of the x and y can be represented by this simple equation x and y. I mean, we can think about this path as a trajectory, which is actually parameterized by at a particular time t. Then, if we can represent the motion of equation of your robot or certain object into the function of the q and t, q is actually mainly position or the orientation. As an example like this, then basically we call it as the holonomic constraint. Then what's the non-holonomic constraint? Non-holonomic constraint is that there are some sort of this differential unit actually they're encoded there. So we need to think about the differential equation. Or sometimes actually there are a lot of theory. We can also transform this equation into something like this. Basically, at a particular position, if we actually, for example, think about a car. You actually driving the car. At that particular position or the velocity, when you are changing your steering angle, in this case, U is actually control. So at the case of the driving car, U is actually steering angle. Then when you are changing your steering angle, you actually position the derivative of your position, the velocity, actually changing. So at that cases, those kinds of cases can be represented by something like this. So in other words, that motion equation consists of the q, position orientation, also the first derivative of q, and then that's actually we call it as the non-holonomic constraint. You can see the main difference between holonomic and non-holonomic cases. So basically, to handle this non-holonomic case, we extend our C space to include this position, the q, position or the orientation, also this q delta is the first derivative. In other words, the velocity of the orientation or velocity of your heading, something like that. This is one of the examples. I'm not going to talk about all the motion equation here since it's already tedious. If you're interested, I recommend you to look at my book. The kinetic car model. You can see the detailed derivation. But again, this actually the theta is the orientation of your car, and then this particular location, and then this pi is your steering angle. Okay, in other words, if you follow certain equation, I'm not going to talk about here. Basically, the heading difference, heading change per unit time, the d theta divided by the unit time difference, delta t, given by the velocity. Velocity over the L is actually constant. L is actually the length of your curve from here to there. and then the tangent of your this pi, the steering angle. In other words, there are basically we need to consider this kind of the differential equation. So that's why it boils down to the non-holonomic constraint actually. And then this pi also the v is kind of this control of your car. So basically, by the changing your this pi, the steering angle, then the theta is changing. The theta in position might be the freedom of your C space. In other words, by changing this the control pi and also the velocity, in other words, you can actually you can kick this accelerator, also the brake, depending on your the control. You actually changing the location of your robot, heading of your robot, basically in the workspace. In other words, you are changing you are changing configuration of your robot. This is one example. Also, there could be another constraint like this dynamic constraint. Dynamic constraint require this q prime, also q double prime. In other words, the second derivative. And this basically when you are considering some of the constraint related to the force. A lot of cases we also have this double this kind of this double derivative. And then it's a little bit basically to consider this kind of constraint, we need to have our C space should be expanded to include this q prime or q double prime. Then our C space getting larger and larger, and it's becoming much more difficult problem. And also there are some of techniques. This dynamic constraint can be reduced to the non-holonomic cases when you are using the sum of extended C space like the state space. For example, basically it's not a very difficult one here. Suppose that here we define the q prime, this tuple as x, new kind of new variable, and then we define the state space as x x prime. It looks like this kind of case, a holonomic case, right? So if you are using this kind of parameterization, and we call this one, when you are using this kind of approach, we call it this state. This is actually a state space. Then dynamic constraint in the original constraint space can be reduced to the non-holonomic constraint into state space. So basically, when you're reading the paper, if you encounter this kind of state space, just think about this concept. So also I'd like to talk about this one. Basically, suppose that we are considering some of the rigid body. I mean, this kind of triangular shape. We have A, B, C. It's 2D position, right? And then basically 3 point A, B, C, and these actually each one has these two parameters x and y, right? So it looks suppose that if you're just using the x, y for A, another x and y B, another x, y C, we're actually using basically six different parameters. Looks like we are using these kinds of six DOF for our C space, right? But as you know, this rigid body we can have we only know the what distance between A and B, right? This actually indicating distance A and B. This is just given by this equivalent distance between A and B, right? And we have the one equation, right? So we already know what are the relations between A and B. They cannot be changed since it's a rigid body. And also we know the relation between A and C and B and C. Basically, we are having this kind of holonomic equation. It does not require this derivative, right? So these equations corresponding to the holonomic cases. And then the main method that I'd like to point out is that each holonomic constraint reduces the one dimension of our C space. Why? It actually restrains our freedom, right? It constrains our freedom. So there are three different equations. This relation, that relationship. Then we actually reduce down the three different parameters. Then looks like it's 60, but in the end, our DOF it turned out to be 3. Okay, so far I talked about mainly this position. Now I'd like to talk about this heading, the orientation of your robot. So we can a lot of cases we need to represent position, also this orientation of your robot. When I have particular orientation, right? Typically we are using this kind of the X, Y, and G frame. We typically call it X, Y, G frame, right? And then the rotating means that I'm rotating my my space, basically my frame space, like this and even like this. So to represent the orientation of the robot, typically we are using the matrix representation. You might heard about S of 3 or SE of 3. When you're reading the paper, a lot of cases actually they're actually using this kind of term. So that's why I'm explaining this concept. S of n indicates the spatial orthogonal group. Orthogonal group S of n of the n by n matrix. It looks like this. Basically, it's n by n matrix. Typically in the series space, it's 3 by 3. But there are 9 different actual parameters. But also we actually have this kind of equation. This equation looks very complicated, but it's a very simple one. In other words, in each column should be the unit normal vector. In other words, their length should be the 1. That's why we have this one. Basically, it's indicating our frame. Each direction, each dimension of our frame should be the unit normal vector, and the two vectors should be orthogonal to each other. That's why we said that orthogonal group. So basically, you can think about this xyz vector in our this canonical space, and changing the orientation actually changing this xyz vector, and then basically at a particular location. So this is actually I'm looking at that direction here, and then like this, and then I can also change like this, right? So based on this xyz, I can actually define this orientation, and then that's why I use basically this three vector indicating our xyz in the 3D space, and then also we also have this particular constraint. This actually intuitively one can represent our orientation with the right hand, or some people can represent the orientation with the left hand. But I want to use only here by this one. I just accepted the right-handed frame. That's why it had the name of spatial orthogonal group S of n. And then also we can think about given this orientation also we can think about this each position, right? We can place a robot here or there, right? That's why we actually have this equation. Given the orientation vector matrix, let's say R of S of n, and then also position vector is here P, and then we call it the spatial Euclidean group of SE of n, and then this 3 by 3 matrix, and 0 and 1. P is actually 3 by this oriented XYZ component of your reference point. We can actually changing it along this direction and that direction, right? That's why we have the actually 3 by 3 vector. Overall, this 4 by 4 matrix. So here, since it's highly likely that you will encounter this concept, is this term when you are reading the paper. I talked about this one. Also, if you want to know more about this one, I already talked about a lot in another book. The series transformation in some of by this book. If you click there, you can see this underlying theory about this one. And then basically for orientation, we can use the 3 by 3 matrix, right? But there could be the nine different parameters. But what might be the actual freedom? You need to think about what's the actual freedom, right? We can actually changing that direction, one direction. I mean, basically there could be many ways, but you can easily see that there could be only three different three DOF actually. Long time ago, already OLX proved that the parameterization orientation can be given by the three value. For example, to define any orientation, we actually rotated this frame along this G space, G direction, high, and along this space, and then also changing that space again. Then we can represent any orientation in the 3D space. There could be many other way of explaining. There are only 3 DOF for representing this orientation. But why is 9? So if you look at this equation, basically here, even though there are nine parameters, we already mentioned that every vector should be unit normal. So there's 3 different equations. Everything should be also on each other. So that's why there are another 3 different constraints. 6. So if we actually, even though there are 9, we take it out. We actually have the holonomics, the 6 equation of the holonomic cases. For determinant, this is nothing but we are taking this space or that space. It does not reduce the freedom. So that's why even though we are using the 9, there are only three different freedom. And also there, one can use this kind of one can use this Euler angle. The more common one is the 3x3 matrix, but much more common one is that also the useful is this cotton iron. I'm not going to talk about all the details of cotton iron, but its main idea is that we represent the rotation in like this. Basically, we think about a certain vector, basically rotation axis, and then we rotated our we represent the orientation by rotating like this, something like this, right? And then so this is actually the particular orientation. Also, we can look at I can look at you that direction. This is my orientation, but also I can look at you like this and that direction. So that's why actually I had this one. This vector nx, ny, ng, three parameter. Also this angle. So there are about 4 different parameters. But the issue is that everything should be the unit normal. So that's why we have another this kind of constraint. And then this boils down that there are only 3 different the freedom. And then this actually these are the low level details of unique cotton ion. If you're interested, if you Google, you can find a lot of information. But I'm not going to talk about the kind of low level details here. So a lot of cases that I assume that you will use the library of using the cotton ion library. So that's why when you encounter that one, at least you can if you know the concept of cotton ion, it's fine. If you are if you want to improve cotton ion, then I recommend you to study more about cotton ion. Cotton ion has a lot of benefits. It's compact compared to this 3x3 matrix, right? The 9 variable. But cotton ion has only the 4. It's compact, and also there are no singularity. So basically, you can think about it this kind of gimbal, and then you might see that this kind of device in the book, right? We can actually base this one. We can change the orientation along x and y, z direction. But at the cases, it's like the Euler angle base or the 3x3 rotation matrix. But at a particular location, every this ring can be aligned into one space. Then basically everything aligned. Then we can only represent we can rotate it that direction or that direction. But we are losing one freedom. So basically the gimbal line indicating 2 axes aligned, and then we are losing a certain freedom. Then somehow we cannot represent. We are losing the freedom. That's actually a singularity issue. Because of that, there could be some of the error. But if you are using the cotton ion, we don't have that problem. But anyway, in the 3D space, our x, y, z, the reference point has a 3 dimension. The spatial orthogonal group of the 3, in other words, orientation, there could be another 3 parameters. Overall, the position and orientation has a 6 DOM. Okay, so far I talked about some of the definition of example of C-space. Next time I talk about the obstacle passes, some other metrics which are actually important, which are related to this C-space. Again, if you have any, you need to come up with the question and write down through the link, write down 2 times before the midterm exam, and then browse 2 paper and submit their summary online before the every Tuesday class through this link. That's it. Thanks so much. Bye.